Professor Belfrost's computer science class is back!
Hi, welcome back to my class, and today we are about to continue our last lesson on the introduction to computers components. And today we are still going to discuss about input and output because we haven't finished that part yet, the last part of the input and output. But before that, I will try to explain some terminologies that we will need when we discuss the next components about processors and also the memory. Okay, so actually, yeah, the first thing that we need to do is just review a few concepts that we discussed on our last lesson. So a computer system consists of four main parts: hardware, software, data, and users. The first one, hardware. It consists of the mechanical parts that make up the computers as a machine required for input, output, storage, and processing of the data. The second is software. Software is just a set of instructions that tells the computer about the tasks to be performed and how these tasks are to be performed. So a set of programs and documents are collectively called a software. The third one is data. So data are isolated values or raw facts which by themselves have no much significance, and this data is used and provided as input to the computer, which is processed to generate some meaningful information. And the last one is users. So users are basically people who write computer programs or interact with the computer, just an ordinary users. Okay, so that's it now for the review, and let's start our discussion for today's lesson. So the first one I want to emphasize here is there are two important terms when we are discussing about computers. There's computer organization and computer architecture, and I will make this clear for you today. So when we are saying about a computer architecture, it refers to those attributes of a system visible to a programmer or attributes that have a direct impact on the logical execution of a program, while a computer organization refers to the operational units and their interconnections that realize the architecture specifications. So, um, the computer organization and computer architecture are actually two concepts that are related to each other. Let's see the example so you'll understand it more comprehend. Okay, so the examples of architecture attributes include the instruction set, the number of bits used to represent various data types like numbers, characters, also the IO mechanisms and techniques for addressing memory, while organizational attributes include those hardware details transferred to the programming such as control signals, interfaces between the computer and the peripherals, and the memory technology that is used. Okay, so for example, this is the general example. It is an architectural design issue whether a computer will have a multiple instruction, but it is an organizational issue whether that this instruction will be implemented by a special multiple unit or by a mechanical that make repeated use of the add unit of the system. Okay, so we are done with uh, computer architecture and computer organization. If there's something that you need to know more, just left comment. Okay, so the second set of terms that I want to discuss is um, about a hierarchical system of a computer. So a computer is just a complex system of millions of elementary electronic computers, electronic components, not computers. Okay, so we need to describe them by using the hierarchical nature. So a hierarchical system of a computer is a set of interrelated subsystems, each of the latter in turn hierarchical in structure until we reach some lowest level of elementary subsystem. At each level, the system consists of a set of components and their interrelationships. Okay, so components and interrelationship. The behavior at each level depends only on a simplified abstracted characterization of the system at the next lower level. And there are two important terms that we need to pay attention here. The first one is structure. So structure is just basically the way in which the components are interrelated, and the second one is functions. Function is just the operation of each individual component as part of the structure. So both the structure and the function of a computer is simple, as there are only four things. First is data processing, second is data storage, the third one is data movement between itself and the outside world, as the computer's operating environment consists of many devices that serve as either source or destination of the data. So there happen process or input output, and the devices revert as peripheral, while the term data communication used to describe process of moving data over a longer distance or from a remote device. And the fourth one is control. So therefore, first, data processing, second is data storage, the third one is data movement, and the fourth is control. And there are some operations that are related to this point. Okay, let's see the next one. Okay, so here's the general picture for you. Okay, so we can view a computer from its functional view. You can see the operating environment, the source, and the destination of the data. And you can see there are arrows that going to and going out from that description, that caption, I mean that text, is going to data movement apparatus balance, and also is connected the control mechanism balance, and also is connected the data storage facility balance, and also data processing facility balance. Okay, so actually these are the four components that we previously discussed about, and it means that because each of these is actually just a description on the functionalities that can be run by the any structural components of a computer, so it means that actually this can build the computer operation. So for on the right side, you can see there's a picture that I have provided, I have prepared for you. There are four operations that can be done by these sets of units: the movement units, the control units, the storage units, and the processing units. Okay, I want you to learn to pay attention to this picture and learn it by yourself. Okay, so this is the first assignment for you today. Okay, so we are done with that structure and functionalities of computer components, and now we are moving to von Neumann architecture. I don't know if you are free, if you want to pronounce it as von Neumann or von Neumann. Uh, I've heard that many times, yeah, with many pronunciation, and it's up to you. Okay. So the phoneme architecture is very simple. So the programming process could be facilitated if the program could be represented in a form of suitable for storing in memory alongside the data. Then a computer could get its instruction by reading them from memory, and a program could be set or altered by setting the values of a portion of memory. Okay? And this idea is known as the stored program concept, and this is implemented in IES computer. Look at the picture below. Okay, so we have the main memory, which is is has M, yeah, the sort is the M, IO equipment IO, program control unit CC, arithmetic logic unit CA, and both C and CC actually a part of bigger central processing unit or CPU. Okay, so the previous picture is actually to show you the general structure of a von Neumann architecture, which consists of first a main memory which stores both data and instructions, and second is an arithmetic and logic unit ALU capable of operating on binary data. The third one is a control unit which interprets the instruction in memory and causes them to be executed sequentially, except for there is some jump instruction or whatever that cause the instruction is not executed sequentially. And the fourth one is input and output equipment operated by the control unit. And so the control unit is a very important part of a computer. Okay, so there are five important points I want you to pay in this architecture. The first one is that this volume architecture, okay, any computer that's built using this architecture, it will have to perform the elementary operation of arithmetic most frequently, yeah, which are addition, subtraction, multiplication, and division. Thus, a central arithmetic part of the device will probably have to exist, and this constitutes the first specific part that you see that you see at the previous picture. This is the CA. Okay. Second, the logical control of the device, which does proper sequencing of its operations, which has to be elastic, and that is as near as possible all purpose that can be done. Then a distinction must be made between the specific instruction given for defining a particular problem and the general control organs which see to it that this instruction, so no matter what they are to be carried out. Okay. The former must be stored in some way, okay? The latter are represented by definite operating parts of the device. By the central control, we mean this latter function only, the second function, and the organs which perform it from the second specific part, which is CC, okay? And you have noticed before, I have described it before, that CA and CC together build a CPU, okay? So any device which is to carry out long and complicated sequences of operations, specifically of calculations, must have a considerable memory. At any rate, the total memory constitutes the third specific part of the device, M, and there are three specific parts, CA, CC together is C, and M correspond to the associative neurons in the human nervous system. It remains to discuss the equivalence of the sensory or aberrant and the motor or afferent neurons. Okay, so it's just the equivalent. Okay, it's the input and output organs of a device, the computer itself. Okay, so the device must be endowed with the ability to maintain I/O contact with some specific medium of this type, and the medium will be called um, the outgoing medium of the device, which is R in the previous picture. That's just symbol. Okay. The next point is that the device must have an organ to transfer information from arm into specific parts C and M, and these organs form its input, the fourth specific part I. It will be seen that it is best to make all transfer from R by I into M and never directly from C. Okay. We'll also see what is the reason for it. This will be our next lesson. Okay. The device must have organs too to transfer from its specific parts C and M into R, and these organs form its output, the fifth specific part O. So it will be seen that it is again best to make all transfers from M by O into R and never directly from C. Okay, so after I tell you about the five important points in this architecture, there are only three main concepts of von Neumann architecture. In summary, the first one is that data instructions are stored in a single read-write memory. The second is that the contents of this memory are addressable by location without regard to the type of data contained there. And the third is execution occurs in a sequential fashion unless explicitly modified from one instruction to the next to the sequential instruction. Okay. Before we move to the CPU discussion, yeah, let us finish up the discussion of I/O from last lesson. Yeah, because previously I just tell you about what components in the computer that is categorized as I/O. Yeah, you have known it. You have learned so much about that, and that's good of you. You can try to search for more information about it. I'll not cover it furthermore. Okay. Now we will go to the most important concept, which is I/O module. Actually, this is just a complementary. Okay, so the computer system I/O architecture is its interface to the outside world. This architecture provides a systematic means of controlling interaction with the outside world and provides the operating system with the information it needs to manage I/O activity effectively. There are three principal I/O techniques. First, program I/O, in which I/O occurs under the direct and continuous control of the program requesting the I/O operation. The second one is interrupt-driven I/O, in which a program issues an I/O command and then continues to execute until it's interrupted by the I/O hardware to signal the end of the I/O operation. And the third is direct memory address, the DMA, in which a specialized I/O processor takes over control of an I/O operation to move a large block of data. Okay, so besides having a processor and a set of memory modules, we also need a set of I/O modules. So each module interfaces to the system bus or center switch and controls one or more peripheral devices. Okay. So an I/O module is not just simply a set of mechanical connectors that wire a device into the system bus. Okay, this is not just a regular wire bus. Okay, rather the I/O module is actually quite complex. It contains logic for performing a communication function between the peripheral and the bus. Okay, but there's actually several reasons that you need to know why we don't connect peripherals directly to the system bus. Okay, so first one is because there are wide variety of peripherals with various methods of operations, and it will become impractical to incorporate the necessary logic within the processor to control a range of devices. Okay, that's the first one. The second one is that the data transfer rate of peripherals is often much lower than that of the memory or processor. Thus, it is impractical to use the high-speed system bus to communicate directly with a peripheral. On the other hand, the data transfer rate of some peripheral is faster than that of the memory or processor, and this is also ineffective. Okay, again, the mismatch will lead to inefficiency in not managed if not managed properly. Fourth, the peripherals often use different data formats and word lengths that the computer to which they are attached. Okay, these two data formats and word lengths it will become one of our discussion in the next lesson. Okay. So actually, this I/O module is very important, and uh, this module has two major functions. The first one is the interface to the processor and memory via the system bus or center switch, and the second is interface to one or more peripheral devices by tailored data links. Okay. Okay, so here is the general picture that can give you for the generic model of an I/O module. Okay, you see the I/O module. You have control bus. It's connected to control bus, control lines, also data lines and address lines. Okay, address data and control lines actually part of system bus. Okay, and the bottom part is you can see there are many links to peripheral devices. Okay, let's explain the picture. As has been taught to you before, the external device is connected to an I/O module is often referred to as a peripheral device or just a peripheral. So there are actually three broad classifications for this. First is human readable, which is suitable for communicating with the computer user. For example, video display terminal, VDTs, and printers. Okay. The second one is machine readable, which is suitable for communicating with equipment. Okay. For example, magnetic disc and tape systems, sensors, and actuators when you use in robotics application. Okay. And the third one is communication, which is suitable for communicating with remote devices. Okay, so these devices, the communication devices, the third type, allow a computer to exchange data with a remote device, which may be a human-readable device, such as a terminal, a machine-readable device, or even another computer. Okay, so okay, this is your second assignment. The nature of external device is shown below. Okay, I want you to uh, pay attention to this picture and try to find more information on other literatures about this picture and write it down in your own word. I mean, describe this picture in your own word. Okay? I will try to explain a little for you. Okay? Okay, so actually, this picture just tell you that the interface to the I/O mode is in the form of control, data, and control signal. Control signals determine the function that the device will perform, such as send data to the I/O module, import read, accept data from the I/O module, output write, report status, or perform some control function particular to the device. For example, position of a disk head. Okay, the data are the form of a set of bits to be sent through or received from the I/O module. Static signals indicate the state of the device. For example, are ready or not ready to show whether the device is ready for data transfer or not. Okay, so a control logic associated with the device control the device's operation in response to the direction from the I/O module. Okay, so the transducer just converts data from electrical to other forms of energy during output and from other forms to electrical during the input. Okay. Typically, a buffer is associated with the transducer to temporarily hold data being transferred between the I/O module and the external environment. A buffer size of 8 to 16 bits is a common one. Okay. Okay, so there are some major functions or requirements for I/O module. which fall into these five following categories. The first one is control and timing. The second is processor communication. The third is device communication. The fourth is data buffering. The fifth is error detection. Okay, so let's explain one by one. Let me explain one by one. Okay. So for the first one, the control and timing, it is needed to coordinate the flow of traffic between internal resources and external devices. Okay, so second one is processor communication. Yeah, actually, processor communication involves these four. First is command decoding. Yeah, so the IO module accepts commands from the processor, typically sent as signals on the control bus. Okay. The second one is data. So there are exchanges between the processor and the IO module of the data bus. The third one is status reporting. Okay, so because peripherals are so slow, it is important to know the status of the IO module. Okay, for example, yeah, if an IO module is asked to send a data to a processor, it may not be ready to do so because it's still working on the previous IO command, and this fact can be reported with a status signal. Okay, so we need to halt for the operation. Okay, we need to wait until the previous operation has been completed. That's the word. Okay, so yeah, current status signals are busy and ready. The fourth is address recognition. Just as each word of memory has an address, so does each I/O device actually has an address, okay, to address it. Thus, an I/O module must recognize one unique address for each peripheral it controls, or if it is module sets, it has a set of unique addresses. Okay. Next point I want to tell you about is that an I/O module must be able to perform device communication, which is this is the third one, right? Okay, so I/O module also must be able to perform device communication. Okay, this communication involves commands, status information, and data. Okay, so data buffering. Data buffering is actually a very important concept, okay? Because whereas the transfer rate into and out of memory or the processor is quite high, the rate in orders of magnitude lower for many peripheral devices, and it covers a wide range, okay? So data coming from memory are sent to an I/O module in a rapid burst, and the data buffer in the I/O module and then sent to the peripheral device at its data rate. Okay, so we need the buffer of data. Okay, so an I/O module is also responsible for error detection too, and for subsequently reporting errors to the processor. Okay, one class of errors that mostly uh, happens is mechanical and electrical malfunctions. Okay, another class consists of unintentional transistor bit pattern as it is transmitted from device to I/O module. Okay, some forms of error detecting code is used to detect transmission error. Okay, so we have what called a parity bit on each character of the data. It is to secure the data in case that there is something error that it can be reported back. So the data can be asked to be transferred back. Okay, so that's the function. We will have a dedicated lesson to discuss more about parity bit. Okay. Okay, so though there are various I/O module structures, we can give a general description about the general I/O. Okay, so the module connects to the rest of the computer through a set of signal lines. Okay, for example, system bus lines. Okay, then data transferred to and from the module are buffered in one or more data registers. There may also be one or more status registers that provide current status information. A status register may also function as a control register to accept detailed control information from the processor. And then the logic within the module interacts with the processor via a set of control lines. The processor uses the control lines to issue commands to the I/O module. Some of the control lines may be used by the I/O module, and the module must also be able to recognize and generate addresses associated with the devices it recognizes and also giving the control to the device. Okay, so for this to be able to happen, that each I/O module we must assign them a unique address. Okay, or if it control more than one external device, then a unique set of addresses is necessary. Okay, Finally, the I/O module contains logic specified to interface with each device that it controls. Okay, I want you to pay attention to the next slide. So this is the block diagram of an I/O module. Now, this is the general picture, and also this is your third assignment. I want you to describe this as well as possible. Okay, so surely, certainly you need to find more information on other literatures that is not given. Okay. Now we enter the discussion about three techniques that generally used in I/O operations. Okay, so here's the overview. The detailed explanation will be on the next lesson. Okay. Okay, so there are three: program I/O, interrupt driven I/O, and also DMA, right? Okay. Okay, so first one, program I/O. So with program I/O, the data are exchanged between the processor and the I/O module. So the processor executes a program that given it direct control of the I/O operation, including sensing device address, sending a read or write command, and transferring the data. Okay. So when the processor issues a command to the I/O module, it must wait until the I/O operation is complete. If the processor is faster than the I/O module, this is wasteful of the processor time. Okay. The second type is interrupt-driven I/O. Okay, so the processor issues an I/O command, continues to execute other instructions, and is interrupted by the I/O module when the latter has completed its work. With both the first and the second type, okay, the processor is irresponsible for extracting data from main memory for output and storing data in main memory for input. Okay, so because this is actually a problem for today's computer, so we are about to be introduced the third method, the alternative, which is known as the DMA, which stands for direct memory access. Okay, so in this mode, the I/O module and main memory exchange data directly without processor involvement. So this is of good for certain tasks. Okay, so here are the summary table of I/O techniques and their relationship. I want you to take a screenshot of this table, and this table will be our basic to discuss the next lesson. Okay, so next week we'll explore these three techniques in more detail, plus introduce you with processor. And we are done with today's lesson. Okay, so the assignment is actually simple. Uh, I don't know if I have assigned you this before, but I want you to again try to find more information if I have assigned you before this assignment. But if not, yeah, this is new assignment for you. Okay, I want you to try to explain using your words this diagram that I've prepared. Okay, so I think that's the assignment. That's enough for today's lesson. A little inspiration for me. So Marcus Aurelius once said, "The happiness of your life depends on the quality of your thoughts." So yeah, you are about your mindset. Okay, your mindset will guide you to your future. Okay, so always be aware of your mindset. Okay, so I think that's for today. Thanks for watching. And here's your to-do list. Subscribe, give a like, comment, and share this video to your friends. My class will be on every Monday, so keep watching and be thoughtful. See you all, and goodbye. Have a nice day.